You have almost certainly seen a black hole, a glowing orange ring hanging in the dark. That photograph was real, and it was historic. It was also a black hole in another galaxy entirely. The one at the center of the galaxy you live in had never been photographed, not once. For half a century, we were certain it was there without ever seeing it. So here is what you are about to find out. How anyone proved that something invisible sits at the heart of the Milky Way. Why the sharpest telescope on Earth came nowhere close. What it took to turn the whole planet into a single camera, and what the picture showed when it finally arrived. One question hung over all of it. Two completely different methods were about to measure the same object. If their answers disagreed, something in our physics was broken. But there is a simpler problem first. How do you photograph the one thing in the universe that gives off no light at all? A black hole is not a hole, and it is not a cosmic vacuum cleaner. It is a region where gravity has become so extreme that nothing gets out. Not a rocket, not a signal, not light. The boundary of that region has a name, the event horizon. It is not a surface you could touch. It is the last line where turning back is still possible. Cross it and every path leads inward. The one at our galactic center is enormous. Its event horizon would fit inside the orbit of Mercury with room to spare. Around most black holes there is a second feature, an accretion disk. That is gas and dust pulled into a swirling orbit that heats up as it falls. Friction and magnetic fields tear at that gas until it glows. The black hole stays dark while the material queuing up around it shines. That glow is the only thing a telescope can ever catch. Which raises an obvious problem. If we can only see the glow, how would we know the darkness in the middle is real? The answer is a shape. Gravity that strong bends the path of light around itself. Rays that should have flown past curl toward you instead. So the glowing material behind the black hole gets wrapped around the front. You end up with a bright ring and a dark bite out of the middle. That dark bite has a name too. The shadow. It is not the horizon itself, but a slightly larger silhouette carved out by bent light. And here is the useful part. The size of that shadow depends on almost nothing except the mass. Measure the shadow, and you have measured the black hole. Which is a beautiful idea on paper. Somebody still had to find one close enough to look at. So point yourself toward the constellation Sagittarius on a clear summer night. You are looking at the center of the Milky Way and you cannot see a thing. Dust in the galactic plane blocks almost all visible light, but radio waves pass straight through. In the 70s, astronomers found a strange compact radio source sitting right at the middle. They called it Sagittarius A star. For decades, that was all it was, a dot of radio noise from about 27,000 light-years away. That distance is hard to feel, so try this. The light arriving from there tonight left before anyone on Earth had planted a single crop. Then came the slow experiment. Starting in the 90s, two teams photographed the same tiny patch of sky year after year in infrared. They were not watching the dark spot. They were watching the stars around it. And those stars were not drifting. They were whipping. One completes a full orbit in about 16 years, while our own sun needs 230 million years to circle the galaxy once. Watch a star swing around something and the maths hand you the mass of whatever it circles. The answer came back the same every time. About 4 million times the mass of the sun. Now squeeze that into the volume those orbits allow. 4 million suns crammed into a region about the size of our solar system. There is no known way to pack that much mass into that little room and have it stay anything else. A cluster of dead stars would collapse within a few million years. It had to be a single black hole. That was the argument for decades, and it was a good one. It was also entirely indirect. So what would it actually take to see the thing? Here is the number that stopped everyone. The shadow should cover roughly 50 microarcseconds of sky. That is the width of a donut sitting on the surface of the moon seen from your back garden. No optical telescope ever built comes close to that. Neither does any single radio dish that can physically stand up on Earth. Resolution comes down to one thing. The wider your dish, the finer the detail you can split apart. To see a donut on the moon, you would need a dish the width of a planet. You cannot build that. But you can cheat. The trick is called very long baseline interferometry. Point telescopes all over the world at the same target at the same instant and record the raw radio waves with atomic clocks stamping every moment. Then combine the recordings afterwards. The waves interfere and the pattern depends on the distance between the dishes. Two telescopes on opposite sides of the planet act like two fragments of one enormous mirror. You do not get the light-collecting power of a planet-sized dish. You get its sharpness, and sharpness was the whole problem. In April 2017, that array went live. 8 observatories at 6 sites pointed at the galactic center on the same nights: Chile, Mexico, Hawaii, Spain, Arizona, and the South Pole. 8 telescopes had to stare at the same speck on the same night. If you enjoy what people build when the universe refuses to cooperate, subscribe. So what did all those dishes actually record? Each station poured raw data onto hard drives at 32 gigabits per second. That is roughly a feature film written to disk every single second for hours on end. The pile was far too big for the internet. The drives were flown across the world and stacked in one room. The South Pole set had to wait months for the Antarctic winter to end. Then the real work started, because the array does not hand you a picture. It hands you a puzzle with most of the pieces missing. Luckily, there had been a rehearsal. The same array had pointed at a second target that same week. M87 is a giant galaxy so far away that its light left before the first primates existed. Its central black hole is a monster, roughly 1,500 times heavier than the one in our galaxy. And yet in our sky, the two look about the same size. That one is gigantic and absurdly far away. Ours is smaller and right next door. The two effects almost exactly cancel. In 2019, the picture of M87 was released, and it went everywhere. A fuzzy orange ring around a dark center. The first direct image of a black hole in history. This is where most people quietly filed the story away as finished. We photographed a black hole, so we have seen one. But that ring belongs to a galaxy you will never visit. The black hole in your own galaxy was still a blank. Same array, same week of observations, no picture for another 3 years. Which is strange when you think about it. Ours is 1,000 times closer. Why would the near one be harder? Because size sets the clock. A black hole that big is also that slow. Gas orbiting the M87 monster takes days to weeks for a single lap, so its picture holds still. Gas orbiting ours goes around in minutes. A full lap near the edge takes somewhere between 4 and 30 minutes, less than a lunch break. So the target was changing while they photographed it. Picture a long exposure of a child running around a room. There is a second problem. Between us and the galactic center lie thousands of light years of thin ionized gas that scatters radio waves like frosted glass. The blurring is mild, but it is not zero. It had to be modeled and stripped out before anything could be trusted. And then there is the last insult. This black hole is faint. For all that mass, it shines only about 100 times as brightly as the sun. Put it in another galaxy and nobody would ever notice it. That makes it the faintest black hole for its size that anyone has measured. It is not feasting. It is barely nibbling. Winds from about 30 massive nearby stars fall toward it. Only around 1% of that gas ever makes it in. The rest gets thrown back out. So the team had a variable target that blurs and barely glows. 5 years of analysis went into what came next. So what does the center of our galaxy actually look like? In 2022, the image was released. A bright, thick ring of radio emission with a dim hollow at its heart. Not one picture, thousands. Different algorithms and different assumptions run independently so nobody could see what they wanted to see. Over 95% of them came out as a ring. When the two best nights were combined, every single reconstruction did. The ring measures about 52 microarc seconds across. Back to the donut on the moon. Run that angle back through the distance and you get a mass of about 4 million times the sun. And that is the moment the whole thing lands. Decades earlier, the orbits of distant stars had given the same answer. About 4 million suns. Two measurements with nothing in common. One from starlight traced over 20 years. One from radio waves bent around an event horizon. They agree. The dark center matters as much as the bright ring. A solid surface down there would make infalling material pile up and heat up and glow in infrared. We would see that glow. We do not. The hollow stays dark, which is exactly what an event horizon should look like. The shape and size also throw out a stack of alternatives. Certain wormhole models, certain naked singularities, certain exotic stars pretending to be black holes. All of them predict a shadow the wrong size. The simulations narrowed things further. 200 computer models of the swirling gas were tested against the data. Viewing the disk edge unfailed. Black holes with no spin failed. Disks orbiting backwards against the spin mostly failed. What survived was a black hole seen fairly face-on with the gas going round the same way the hole itself turns. It is worth being straight about the limits. This matches Einstein's description of a spinning black hole, and it kills off several rivals. It is not final proof of every detail. In fact, not one of the 200 simulations passed every single test. The real thing was calmer and steadier than any model predicted. Something in the physics is still missing. That is not a failure. That is the part where science gets interesting again. But hold on to what actually happened here. For the whole of human history, the center of our galaxy was a direction, a smudge behind dust. People built monuments pointing at it and never once saw what was there. Now there is a photograph. A ring of light bent by an object so dense that it has torn a hole in the geometry of space. Everything you have ever known circles that thing once every 230 million years. Last time around, the first dinosaurs were only just appearing. It took 8 telescopes and 5 years of argument for our species to finally see it. We turned the whole planet into an eye. And what it found was the dark heart we have been circling all along.